voice. It's bad today. Please excuse me for that. So today my presentation is about challenges in reliability screening for high power diodes. And I come from Chengdu University and from Center for Reliability Sciences and Technologies, which is the first comprehensive center established in Taiwan. So now this will be my outline of the presentation, where I will talk about a little bit on what is the motivation and the introduction about the presentation. Then I have used finite element modeling for my analysis and some methods used to extract data from the finite element modeling, and then simulation results and discussion. After that, I'll conclude my presentation following with the acknowledgement. So moving on the introduction part, the basic motivation behind doing this work is to establish a method by which we can screen out high power diodes after the packaging and the product is ready, because in one day maybe there are several thousands of power diodes being manufactured, and we need to find out a suitable screening method so that we can screen all of them, because if we have a screening method which takes even more than 1 second, so it's like number of diodes produced multiplied by that time which will be required to screen out those power diodes. So there has to be a suitable method which can be very quick yet efficient. So we're looking into that. And so this is a very basic structure for high power diodes, where we have a silicon die and have both side layer of solder with a copper lead, and this whole structure is surrounded by the ceramic package. And now we have two directions, as we can see from the black arrow. The current goes from one end and goes out from the other end, whereas the heat flow is from the both sides. When the high power is working in field, so it can heat up because of the junction temperature, so the heat can flow in both directions. And now, as we know, in high power diodes there is a high level carrier reaction, which is a very common phenomena. This can cause to rise in the thermal junction temperature, following with the high thermal resistance will make it worse, and hence there will be a poor heat dissipation and the electrical characteristics can be altered because of that. So also this phenomenon is very commonly seen, where there is shift in the VF value because of the temperature of the junction temperature of the diode. So you can see that there is a variation in the temperature with respect to the shift in the VF, and a similar kind of shift we took some power diodes from a company, and we used a Mentor Graphics 3 stir machine to evaluate the thermal resistance of those power diodes. And we also see that with change of these thermal resistance of the complete power diode with the package, we can see a shift in the VF. So what we thought was, from the theory, there has to be certain kind of relation between the RTH and the VF also. And this was the work done before, where del VF method was used to screen out those power diodes, and it was very efficient to it was very efficient to separate out those diodes which had these black dots and the triangles. They show the good dyes, and whereas these are the ones with voids in the solder. So this method is very nice to screen out those diodes which have in which the solder have voids and the other ones are good. So we followed on this, and now while VF is used, we can use other methods also. For example, we can use series resistance, we can use other parameters of diodes for screening out, but then evaluating those parameters again takes a lot of time. So LVF is quick because industry standards use 70 milliseconds, like they give the power load, and then once the load is off, they calculate the del VF for after 70 milliseconds, and then they get the value. So this is very quick, and we can screen out this efficiently. Now, following the same literature, we also did some experiments. We tried to plot the del VF versus RTH for the diodes we have. Now, what we found was, if not more, at least we should have some trend. The screen line is that expectation, could be linear, could be some other trend, but we expect some kind of trend between del VF and RTH. Whereas the red dots show the experimental values, which was all scattered. There was no such trend found, but from the theory, from understanding, we expected some kind of trend to be there. So now this poor correlation between del VF and RTH is very important to understand, and maybe this can help the industry to find a suitable method or suitable way of screening out the power diodes. So we investigated our work uses finite element modeling to understand this poor correlation between LVF and RTH. So how we go about it is we have this simple structure, and what we do is we try to introduce some air bubbles like voids of 1 to 20 micrometer diameter, and these voids are placed randomly inside the solder layer. And we try to keep, even though the geometry is a bit different from the industrial diode, but we try to maintain the total net thermal resistance of the structure by adjusting the properties. And this is the finite element model we did. We use ANSYS workbench, and we are using a model from the industry standards of a 75 mil diode. And what we do is we keep these thin solder layer at the top and bottom and a thermal conductor, which is mimicking the normal diode where we have a diode sandwich between solder and the copper leads. And the insulators all around are like the package, ceramic package. Now this is, after we did the element modeling and we got the results, we also, now in future we are thinking of really mimicking completely, because what we found later on that these corners are still exposed. So in future we'll try to cover up this, we'll try to cover up this area also so that it can really be mimicked like a real diode. And the properties that we use are very, normally you can find these properties everywhere, but the important part here is the thermal conductivity, which is variable. Now this variability of thermal conductivity comes in either because of the solder voids that we intentionally introduced inside the solder layer, or it could be variation of the RTH that we can also intentionally, we can change the properties and we can vary the RTH for the particular layer. So the method is very simple. We obtain the temperature versus time curve. Now this temperature versus time curve is a transient analysis. We obtain the curve, and then in ANSYS simulation, and then we use this curve to convert this temperature versus time to del VF versus time. And we use a classic 2 millivolt per degree Celsius relationship for silicon diodes, silicon chips. And it's not exactly 2 millivolt that I use in my experiment, because just to confirm to be accurate, I first use again the Mentor Graphics G3 stir equipment to find out the relation first. We first calibrate the particular diode for VF versus temperature, and then we find the slope of that curve. So that slope is somewhere around 2 millivolt only. It's like sometimes it's 1.7 millivolts, sometimes 1.8. It's very close to 2 millivolts. So we use that relation for individual diodes, whichever measurement we are taking, and then we take that into account. And then after we get this LVF versus time curve, we extract LVF for different RTH values at a given time, and then we plot LVF versus RTH. It's a very simple method that we use. Now, so this is my simulation results. The orange curve that we see here is the load and this load is a conventional TV load, again used by the company, and we had a lot of discussions. So what kind of load we should use? So we discussed with them, and we use this kind of load which is used in TV applications, and it is a transient analysis where each and every point of the load is corresponded by the results that we get. Now in this result we have three main elements. Okay, so I'll share one by one. So this curve for different colors is for variable RTH, some with voids and some without voids. Now the first part to discuss is about this initial region, which is somewhere less than 10 milliseconds. So in this region we can see that the curves which have voids and the curve, this straight curve belongs to the one without void. So we can see a clear distinguished curve, so we can differentiate, we can screen out those diodes with and without curves, without solder voids very easily, as shown by the previous values also. But this work is considering the RTH into account, not only del VF, but it's del VF and RTH both. So we can very well screen out those diodes at a very early stage if we really want to screen just on the basis of whether it has voids or it does not have voids. Second region is this region, which lies between about 10 milliseconds to 25 milliseconds. Now here we can see a clear distinguished curves for the ones which have variable RTH also. So it's not only those diodes which have solders, but those diodes which have solder voids and also have variable RTH. Those also can be screened out and can be differentiated on the basis of temperature. And the third region is this 40 milliseconds, this point, and the 70 milliseconds, this point. This region where normally the industry uses 70 milliseconds for del VF measurement. So we can see all the data points here are merged for the variable RTH, and also the difference between the ones with and without void is very less as compared to the first region. So what we see from here is that if we can do our RTH, del VF measurement at early stage, we can really screen out those diodes. And if we do it at a later stage, it gets mixed up. As we can see, if I extract those RTH values, del VF values for individual 40 milliseconds and 70 milliseconds, I get these kind of curve. Now, these points which are at the top belongs to solder without any voids, but have variable RTH for sure because we induce those properties. And the ones with the voids have this planar kind of curve, which really shows that if we extend our detection time for del VF for a long time, then it becomes ineffective. Now, just to compare what I got in my experimental data and what I got from the simulation, it's almost like correlated. We have these random values initially and then this planar one, and same here. Now, the solder without any void have these kind of relationship. We are still trying to investigate because there could be other factors, maybe coming up from the shape of the solder that we use, or the insulator properties, or the complete coverage of the diode with respect to the package. We are still investigating the reason why we have this, but what we can conclude from here is the del VF versus RTH plot for 40 milliseconds or even 70 milliseconds is not effective to screen out my diodes. So that's what I said, that 70 milliseconds, the data that I got from the experimental results, we are able to simulate and then reproduce those data. And scattering of the attributed samples without solder voids are still under investigation. And screening is ineffective for samples. Is effective for samples with solder voids, which is mainly due to larger detection time. Now, from this, I can also understand that if I give a lot of time, because normally for RTH measurement, after the load, it is allowed to cool down, and during that cooling phase, when it is the RTH measurement is done. So if I give a longer time for the RTH and the del VF measurement, then it's like it's almost all of this. The temperature becomes stable by a larger detection time. So at initial phase, there is a difference between how the temperature profile is depending upon variable RTH. That is the sweet spot where we can find the correct screening of the del VF. So to summarize and conclude, poor correlation between del VF and thermal resistance has been established for high power diodes. We use finite element modeling to understand the lack of correlation. And it is a large detection time which is found to be the main culprit for the poor correlation. And even though del VF test is a good screening method, but when we consider thermal resistance also with respect to del VF, then it becomes a big problem unless we really take care of the time when we are taking the measurement. And to acknowledge, we really thank Lynas Semiconductor Corporation because we have a joint lab with them for all the support. And I come from Taiwan, and we are based in the north part of Taiwan, which is in between of the Taoyuan airport and Taipei, just in the middle. And this is my group, of course, led by Professor Xiaoming Tan. And I really thank my group for all the support and Professor Tan. Thank you. This is my presentation.
Okay. All right. Thank you. So, any questions from the floor?